All right, class, welcome to the first in our series of video lectures. Unfortunately, I don't have a whiteboard today. I don't think it'll be a big deal because we're not going to be really working with any math, but look forward to seeing a whiteboard and a little more interaction here in the future, okay? All right, let's get started. Today, we are talking about graphs. Graphs are how scientists tell a story, all right? Every graph is it's a language, okay? And if you know how to read them, you can tell what's happened in any given experiment, all right? So let's start at the beginning. In order to talk about experiments, we need to know what an experiment is, okay? An experiment is not a guy or girl in glasses surrounded by beakers and boiling things. An experiment is a process that is used to test a hypothesis. Well, this leads us to, what's a hypothesis? Okay. A hypothesis is an educated guess. Okay? It is a guess that is based on research and prior knowledge. All right? So, going from here, we need to talk about the scientific method. This is the process that scientists, every scientist on the planet uses to test their hypothesis. Okay? It is so critical just to the concept of science, okay? Let me tell you a story. About 2,500 years ago, there were two philosophers, okay, old scientists. They were trying to discuss what everything was made out of, okay? One of them, a really famous guy named Aristotle, thought that everything in the world was made up of the four elements: earth, fire, wind, and water, right? Your breath is made of wind, and you know, you clearly have fire inside of you because your skin feels warm, and you're solid, so there has to be some earth in there. And he thought that everything could be broken down into these four elements, right? There was another philosopher named Democritus who thought that all matter was made up of these little teeny tiny things that couldn't be split anymore, right? He called them atoms. Unfortunately, Aristotle was a better arguer. He was better at debating than Democritus was. So for hundreds of years, people thought Aristotle was right, okay? Because he was a better arguer, right? When we clearly know now that Democritus was right all along, and the scientific method would have proved him right, okay? So remember, science is not a popularity contest. It's not based on any kind of bias, and it's definitely not based on who can make the better argument. The scientific method is based on collecting data, right, and doing experiments. So let's walk through this. Very simply, the scientific method is ask a question. Will plants grow taller if I feed them water or milk? There's a question. You construct your hypothesis. That's an educated guess. You say, I think plants will grow better if I give them milk. You test this with an experiment, okay? So you take three plants. One, you don't do anything to. One, you give water. And the third one, you give milk, okay? You then run the experiment and you collect all that data. So over the course of the next couple weeks, you measure how tall they grow, you take those numbers and you analyze them. How do you analyze data? You put it in a graph. And then you form a conclusion. And all a conclusion is it tells you, was your hypothesis right or wrong? In this case, unless I'm mistaken, the plant that was given water is going to grow much taller than the plant that was given milk. And your hypothesis would be false, okay? In this case, you construct a new hypothesis. Maybe this time you would say, I think the plants that get water are gonna grow taller. You go through the whole thing, and hopefully you come up with a conclusion that's true. And a thing to remember here is getting a conclusion that matches your hypothesis. That's not the goal, okay? This is just an educated guess. If you see something different, you have to recalculate how you see the world. And that's the thing about science, okay? Science is just truth. And we're just trying to use these steps to get at the purest truth that we possibly can, okay? If you want a little more information, I gave you a flow chart here. You guys can work through this. Hopefully this helps you understand it a little bit more, but I'm gonna move forward. Okay, so we need to look at a couple words. Number one, data. What is data, or data, however you call it? Data are your measurements. If you're measuring plant growth, your data is how tall is the plant. You could measure it every day, every week, every hour, whatever you want, but those measurements are data. Data is always, always, always going to be a number. How tall is it? How much does it weigh? How fast is it going? How much force does it have? How many volts of electricity are going through it? Whatever it is, data is always a number, okay? That's important. Graphs are the tools that we use to analyze data, and that's what we're gonna see today, okay? Graphs allow us to see the relationship between two variables, okay? So like, for example, here's a graph, okay? This graph has to do with typing speed. Okay, down here, you have the weeks of practice on your typing, okay? So that's 1 week, 2 weeks, 3 weeks of practice. And here on your y-axis, you have words per minute. And as you can see, there's a relationship. The more weeks that you practice, okay, we see that the words per minute that you type increases. Okay? That makes a lot of sense, okay? This graph shows the relationship between weeks of practicing, typing, and how many words per minute you can type. Now, something that we need to talk about here is that it shows a relationship between two variables, right? So we just need to make sure we understand what this word means. A variable, okay, whenever we have a big word, I like to break it down into smaller words. So look at this. Very able. A variable, the word vary, okay, to vary literally means to change. Okay, if something varies day by day, it changes every day. That's where the word various comes from. It means many, or a variety is many types, right? A variable is literally something that is able to change, okay? And in math, okay, you've seen variables a million times. Variables are always the letters, X and Y, F, M, A, whatever it is. These are all things that can change. Like for example, if X is the height of the plant, well, the height of the plant changes every single day. It's able to change, right? Whereas a constant is something that never changes. And in math, constants are numbers. 5 is 5 is 5 all the time, okay? So that's a good thing to remember. Now, let's quickly talk about what kind of information you need on your graph. A graph always needs a title, which is usually the x-axis versus the y-axis. This is a long, specific title. For that last one, it would have been weeks of practice versus words per minute, but you can make it simpler than that. Your axes always have to be labeled, okay? If you have a blank graph, I don't know what I'm looking at. And not only do the axes have to be labeled, but the units need to be labeled as well, right? If you're telling me that something is let me show you again. Okay, here's your title, okay? It's always at the top. This summarizes what's going on. This again on the bottom is your x-axis. Here, this is going to be time. As we'll see in a minute, time always goes on the x-axis. Always, always. And here is your y-axis, okay? It's always important to label what we're looking at, right? We need to label units. If this was 1, 2, 3, 4, 5, and I'm talking about time, well, what am I talking? Are we looking at 1 second, 1 minute, 1 hour, 1 year, 1 century? I have no idea. That's why you gotta write this here. So in parentheses, you would put second or minute, whatever it is. Same thing with the units. If you're talking about a length, is it an inch? Is it a foot? Is it a mile? And actually, we wouldn't use any of those because, as I'm sure you remember from earlier today, we use meters, centimeters, millimeters, okay? So thanks for catching me on that one. All right, let's move forward here. So there are 2 types of variables that we use, okay? On the horizontal or the flat line, this is the x-axis, okay? And on the vertical line, the y-axis, okay, that's what we call that one. I always remember y goes to the sky. It's the easiest way for me to remember that, okay? This is the x-axis, this is the y-axis. All right, so let's go back here and talk about the variables that go on these axes. All right, on your x-axis, that's the flat one, the horizontal one, we have what's called the independent variable, all right? This is the variable that the experimenter controls. This is the thing that you are changing, okay? For example, let's say I wanted to see how much water I give a plant versus how tall that plant grows, okay? Well, which one of those things am I controlling, right? Am I controlling how much water I give the plant, or am I controlling how tall the plant grows, right? While I wish I had superpowers, I cannot control how tall a plant grows, right? But what I can control is how much water I give the plant, which is why this is your independent variable. You set it. On the y-axis, we get the dependent variable, and it's called dependent, okay, because it is dependent on the independent variable, which is a mouthful, but go back to that water-plant relationship, okay? The amount of water is what I control, okay? I can control how much water I give a plant, okay? But the amount of water you give the plant controls how tall that plant grows, okay? The x-axis determines the y-axis. So for example here's the basic write-up. This is always your x-axis, this is the independent, this is the one that you are controlling, and this is your dependent. That is what ends up changing. So let me give you a few examples here. All right, this one might be kind of hard to see. It's in the PowerPoint. You guys have it on the Google Classroom. But let's talk about a car wash, okay? Here we have the number of cars that we wash, and here we have the revenue, how much money we make, okay? In this case, the number of cars is the independent variable. We control that, or circumstances, maybe the number of hours we're willing to work at the car wash, right? Okay? The more cars we wash, the more money we make, right? It doesn't work the other way. The amount of money we make doesn't determine how many cars we washed, which is, I know, a little brain bending. Let me give you a few more examples. Let me see if I can make this a little clearer. Okay? Here's a really good one. Here we have the temperature measured in Celsius, okay? We'll get there eventually. And here we have the number of sales for an ice cream shop, all right? Now I want you to think about this. Which one of these variables can you control? Do you control, or which one of these variables, sorry, it's not all about control. Which one of these variables affects the other one? Does the temperature affect how much money you make? Or does how much money you make affect the temperature? Let me pause the video and think about it for a second, all right? I'll wait. All right, you good? Well, hopefully you came to the conclusion that the temperature controls how much money you make, right? This makes sense, okay? First of all, we can't control the temperature, okay? It's a good place to start. But the temperature is going to determine how much money you make, right? The hotter it is, okay, the more ice cream you're going to sell. The amount of ice cream that you sell does not determine how hot it is outside, okay? Again, I wish we had these superpowers, but not quite yet. And one more, okay? How much sleep you get before a test, okay, determines the grade that you get on it, or at least helps determine it, okay? The fact that you get an A+ on a test doesn't mean that you only get 2 hours of sleep the night before, okay? But if you only got 2 hours of sleep the night before, you might not get that A+ on the test, okay? The independent changes the dependent, okay? The dependent, here's how I remember it. The dependent variable depends on the independent variable, okay? So, now that we've talked about variables, now we need to talk about relationships and the way that variables can make each other change, okay? The first example is what is called a direct relationship, okay? A direct relationship means that when one variable gets bigger, the other variable gets bigger as well, okay? And this goes back to our plant example, all right? The more water you give a plant, the bigger it will get. The less water you give a plant, the smaller it will get. This is a direct relationship. The other relationship is called an inverse relationship, okay? And this means the opposite. when one variable gets bigger, the other variable gets smaller, okay? I like to think of this as the more money you spend, okay, the smaller your bank account gets, right? And the less money you spend, the bigger your bank account gets, okay? These are always going back and forth. So let's look at the two examples here. Oh, here we go. I have an example for you before I get to that example. Here are your two examples. All right, so here we have the amount of advertising a company does and the amount of money it makes. This is a direct relationship. The more advertising a company does, usually the more money it's gonna make. That makes sense. Whereas here, we have an inverse relationship, right? It's going down. Here, we have anti-pollution expenditures, meaning how much money is a company spending to fight pollution. Well, the more money a company spends to fight pollution, okay, your pollution emissions, how much pollution you have, goes down. And notice, direct relationships, when one gets bigger, this one's increasing, so this one's increasing. Whereas here, as this one's getting bigger, this one's getting smaller, okay? So let's look at how this looks mathematically, all right? And this is gonna be something we're gonna come back to over the whole year. Direct relationships always look like this. X equals Y. Remember, letters are always variables. So if X is the amount of water you give a plant and Y is how tall the plant grows, the bigger X is, the bigger Y is. And this makes sense mathematically. Look at this. If X is 1, well, X equals Y. That means Y is 1. So if X is 2, well, that means now Y is 2 because X equals Y. This is a direct relationship. If X gets bigger, Y gets bigger. If X gets smaller, Y gets smaller, okay? An inverse relationship mathematically looks like this. X equals 1 divided by Y, okay? This one takes a second, but look at it. It makes perfect sense. If X is 1, okay, or if Y is 1, is what this should say. If Y is 1, okay, 1 divided by Y, or 1 divided by 1, you can put in this calculator if you don't believe me. 1 divided by 1 is 1, okay? This should actually say, I got this a little backwards here. Actually, this is right too. If, let's say, if Y is 2, well, X equals 1 divided by 2. And 1 divided by 2 is a half, or 0.5. Meaning the bigger Y gets, the smaller X gets. And the smaller Y gets, the bigger X gets. And I would say 99% of the equations that we're going to see this year are some combination of these two things. Okay? So it's really important to get your mind around that. I'll change this on the PowerPoint before I post it tomorrow, just to make it a little clearer. I'll switch these X and Y's around. Okay, so let's look at the examples from the beginning of class. Okay, so earlier today we looked at shoe size and height, okay? Is this a direct relationship or an inverse relationship? Again, think about this for a second, okay? As somebody's shoe size increases, do you think their height is going to get bigger or smaller? Okay. Well, hopefully you remember that it gets bigger. As one gets bigger, the other one gets bigger, okay? The taller a person is, the more likely they are to have big feet, okay? And vice versa, right? This is how this works, okay? Usually, and this isn't 100% true, right? But it's a good way to kind of remember these things. And the second one I want to throw at you, and unfortunately I'm just now noticing it's all going to come up at once, but that example of cars, right? Earlier we looked at how much a car weighed and how quickly it could go from 0 to 60, okay? And what did we see, okay? The bigger a car gets, okay, the slower its acceleration, right? The longer it takes to get from 0 to 60, right? Whereas the lighter a car is, okay, the faster it's going to accelerate. This is why race cars are always trying to cut weight, because they know that less weight equals more acceleration. Okay? So we're going to stop here for today. Next class, we're going to be talking about the slope of these graphs and what that tells us. You have everything here to to answer all the questions on your quizzes. Again, if you don't understand something, find me at tutoring, shoot me an email, and yeah, I hope you have a great day.